We have looked into shear flow in the last class, and we discussed few detailed work on the shear flow. We said that if you have a load on a structure, like let's say I have a beam, not really a rectangular beam. So let's say I have a channel section beam. Okay, and channel section beam, and that beam is fixed to something. And suppose you have a load P acting on it. Let's say, what would be its centroid? Its centroid is probably going to be something from here and something from here. It's here. So let's say we have a load P acting here. We said that because of this load P, the shear flow that will come to the structure, if I take a cross section here, okay, let's say I take a cross section here, the cross section going to look like this, and there is a point P force here. We said that the shear flow will look like this. It will enter from this side, then it will flow down the cross section, and then it will go out from this side, right? Okay. And we also said the portion that is longitudinal, or that is normal to the load direction, is going to have a linear distribution. So these two are going to have linear distribution, and the portion that is not normal, that is parallel to the load, is going to have a parabolic distribution, right? This is what we discussed. Now, one thing to note is, when I'm drawing this, please note, I'm not drawing exact to this point. Okay, I'm a little bit away. So this is from center line to center line. All diagrams here are center line to center line. This is because this is due to the sections being very thin. So it doesn't matter how much is more stress on this side, okay, or this side. So here also you see there is a little bit left. So it is all from center line to center line. All calculations are based on center lines, not to the end. To note that, okay, to not make a misjudgment there, right? Okay, I will ask, is it teaching and the writing lagging, or that's okay?
Sir, there is no lag between what you write and what you say, but there is some lag between what we say and what you can hear.
Okay, so I think then teaching video will be okay. All right, so you can go through the video. All right, so this is how it looks like, right? The shear stress or the shear flow will look like, and we know how to calculate this point. The maximum and the minimum stresses here. The maximum stress here, the maximum stress here. This is called shear flow. It's not stress. Shear flow has a different unit to shear stress, okay? Right? This is Newton per meter, and this is Newton per meter square. So they're different. And we said that we also saw that cross section I can represent it using only the forces, right? The same cross section. What I can do is I can always represent them with the force. Now, how do I draw the force here? So instead of having, instead of having all the arrows here, I can have a single arrow that represent these forces, right? Sorry, that represent these forces. So this force is going to be called as F flange. This is also F flange, and this is your F wave. Okay. Now, since no external force, sorry, no external force along transverse direction, we have FF minus FF equal to 0, right? So both are going to be equal. But the vertical shear stress, the vertical shear flow, is going to be FW, which is in book they write it as V, is going to be equal to P in this case. Okay, it's going to be equal to V. V is a shear flow, the shear stress. In this case, it is P because we have one point load for a cantilever beam. Okay, clear? We saw that in our last discussion. Now let's say something. Let's look at something here. So I have this section now, okay, which is a channel section. We call it a channel section or a C section, whatever you want to name it, however you want to name it, a channel section. And the channel section has following forces, right? It has a force which is along this, which is called FF. Same FF is going to act here. Then there is a V force, right? And there is an external force P. Okay. All right. Now, if I take a moment of this section about taking moment, taking moment about, you can take moment about, let's say, vertical line V. Okay. What are we going to get? The summation of forces are balanced, but what about moment? Is the moment balanced? If you take about this line, if you take it about this line, or if you take it about this line, either if you take, is the moment balanced? The moment is not balanced, right? Because FF into, let's say this is H, from this center line to this center line is H. FF into H is equal to, let's say this distance is C, equal to P into C. Is not equal to, no, I cannot write equal to here. I can write, this is this direction, that is this direction, right? Minus this is equal to 0. Not 0. I don't know whether it's 0 or not. That's your moment. moment acting on the cross section, right? But please note, external force is applied at the centroid, right, of the channel section. Even if I apply the channel section central load, unless this fellow is 0, I cannot have. Did I do it correctly? Yeah, I've taken moment about this side. So this is going to be this way, and this is also going to be this way. Okay, that's fine. I do not have, may not be 0, right? Because F into H may not be equal to P into C. Okay, clear? Or let's not let's not look from the external and internal load. We can do it based completely based on uh, the internal load, right? So this equation can be written in terms of internal load. That means taking moment about point this, let's say this point is O, taking moment about the line of action P. Then what do we write? We write it as FF into P, not P, FF into H and plus V into C equal to 0. Not 0. You cannot write it 0 because it may not be 0, right? This is the moment. So what happens to this moment then? So if you have a load acting in a channel section along its centroid, the channel section has been seen practically to start deforming like this. Because of the moment, it starts twisting. Because of this moment, a single symmetric section starts twisting. Okay. To arrest this twisting, we need to do something, right? We need to load single symmetric section at a different, what is this going on? A different location. This is called shear center. Location is called shear center. Okay. If we load at shear center, the unbalanced moment at a cross section is 0. Okay, so that's the objective of having a shear center. Now, how do I calculate that? So let's go back to our basic analysis. So we have this again, the channel section here. And we can calculate shear flow, and the shear flow will give us a force, which is this one, FF, this one here, FF, and here it will give a V force, right? Okay, and let's say I have attached a gusset plate here. A gusset plate is something that carries a load outside the section. So this is a gusset plate, and there is a P force acting here. And let's say that makes an eccentricity from here as E. Okay, so load P is applied with an eccentricity E from the center line of the vertical arm of the channel section, or wave of the channel section. Wave is the better word. Wave is very commonly used word, right? Vertical wave of the section. In that case, if I take moment, how will it look like? It will look like now moment, taking moment. We get FF into H minus P into E is equal to 0. Okay? No, what did I do? Not P into E. I have to take moment about taking moment about P, location of load. Taking moment about location of P. What do I get is FF into H minus V into E. 0. Right? I have to make it 0. No twist. That is our objective. So E is equal to, I don't know E, so I have to find out E. So it is going to FF into H by V. Now we know for this problem V equal to P, right? So you can write that is equal to FF to H by P. So that's your shear center. E is the distance of the shear center. E is the distance to the shear center. All right. So is it understandable how to what is shear center? A shear center is a center through which if you pass your vertical load, then there won't be any twist in the cross section. That's shear center. And E is what we need to find for a shear center, and that is given by in this formula. So, but you remember that note, we'll prove it a little later. Note that shear center is a geometric property of a cross section. So you will get that in the handbook itself. The handbook also tells you, gives you where is the shear, what is the value of shear center. Okay, let's quickly do a small problem.
Sir?
So that it becomes,
Sir?
yes, sir.
Sir, basically here the force P is not cancelling the moment, rather at the point only is like important. So why do we have force at that shear center? P force.
Yeah, because unless I have a P force, I cannot balance it, right?
No, sir, but at the point where P is acting, if we at a moment it becomes 0 on its own. So why do we need a P force?
No, why it becomes automatically zero?
Yes, sir. Like,
Automatically zero.
yeah, because there's no P in the moment equation, sir. Force P is not included in the moment equation, but without direction, it
because
becomes
we are
zero.
looking into internal forces. This is balance of internal forces, right?
Yes, sir.
I'm balancing the internal forces, not the external forces. So when you applied a load here, right, externally, your internal loading becomes like this in the channel section, right? Now you want to balance these internal forces. You can see that horizontally they are balanced.
Yes, sir.
Vertically, this V will be balanced with the shear flow that is there, right?
Sir, sorry, sir. Like, your voice is breaking a bit, sir.
But what about? So I'll write it this way. Is equal to QW here, FW here, right? For a moment, if I take in this case, unless I put some, this may not be equal to 0. You have a symmetric structure. It will not be 0 if it is not a symmetric structure. It depends on the value of FF. It depends on the P that you have or V that you have there, W or FW, whatever. It will not come out to be 0. It doesn't come out to be 0 because practically you can see there is a, there will be a bending, there will be a twisting in the structure. And therefore, when you try to balance it, so it's actually problem has come from field, right? So in field, you see that the sections are getting twisted, and then you try to analyze and see, oh my God, the moments are the cross section are not valid, not balanced, and therefore you need to shift your load P from the center line. And how much do you shift? To be guaranteed that the shift should be such that your twist is balanced.
Okay,
Okay, let's take one problem. Yeah.
Sir, just a small doubt, sir. Here, if there is no P force acting, then in which direction will this rod twist, sir? Like,
if there is no force acting on the structure, the rod will
like,
not
no,
twist.
sir. I mean, like, there is no force P acting, sir. Like, we don't have this gusset plate and also. It's just the structure. So, in which direction will it twist, sir? I mean, like, how will it twist, I'm asking, sir? Because you drew a diagram initially, I think, sir, it was like a little bit turned to
If
turn
it
to
is
the
only the
clockwise
structure
direction.
and the P load is acting from the center line, yes, it will twist clockwise because the load is acting here, right? Twist clockwise. Here, it will twist this way. Okay.
Yes. So
some point between
from
from here and here, some point between it will not twist. That point center. Which one?
Yes. Yes, sir. So basically, this column twists anti-clockwise, sir. Am I correct?
No. With the current loading position, it will twist clockwise, not anti-clockwise. The load, external load is here, right? If you give external load here, how it is going to twist anti-clockwise? It is going to twist clockwise only. Imagine that you have a section like this and you have given load. Forget about internal stresses, internal loads. You have a structure like this and you have given an external load here. Which direction is going to bend? It's going to bend this direction only. Right?
Yes, sir.
Even if you put the load here, it is going to bend this direction because that's not shear center. Okay.
Okay, sir.
Right. Let's look at small problem here. Now, this is a channel section with, see, the width are given from center line to center line. This is a center line. This is a center line. Okay. Even height is given from center line to center line. Please note the dimensions are given center line to center line. Okay, we call it at C2C, center line. Right. Okay, so Q, we know that I need to find how the air is flowing through it. Okay, that's why I know the flow Q is given by Q by I. Okay, and I have to calculate and see the calculation of I. Now, please note the calculation of I. I'm doing it from the center lines only. I'm not doing for the whole section because the section is very thin and the error will be very less. Okay, so it's an approximated I. So 1 by 12 THQ. So this is my T and this is my H. Sorry, this is my T and this is my H. So this portion is given by 112 THQ. And for other 2%, I've just added the areas, right? So BT is the area of this portion. BT is the area of the portion. Therefore, there is a 2. And I'm multiplying with the centroidal distance H square, right? So I'm not doing a calculated, doing a little bit more calculation on what will be the I for like BH cube by 12, right? Because it's going to be very, very small, right? Sorry, BT cube by 12. Since T is very, very small, BT cube by 12 will be in the second, another order, maybe in the second order or third order. So I don't care about it. I do this calculation. If you want to care about it, do that calculation. Nobody bothers about it. You can do it, but it will take some time from you. So that comes out to be, I comes out to be this. Okay. Now let's look at, I know that if my load is, then this portion is going to be triangular. This portion is going to be triangular. And this portion is going to be a second order parabola, right? Now, if it is a triangular, I need to find what is the maximum value here. So let's say that is Q1. This value is Q2. And again, this will be Q1. Okay. I have to find Q1. Now, Q for Q1, VQ by IB, I have to find Q for Q1. Q for Q1 is going to be this area, moment of this area with respect to the centroidal line. So what is this going to be? The area here is B into T because this is B into T, and momentum is going to be H by 2. So Q for Q1 is BT into H by 2. Okay. So you can find Q. Q is going to be V shear force at that location, which is V. And then Q I have found out BT H by 2 and then divided by I. And I is TH square by, that is also found. Going to be your, now what will be your FF is the force integral of this whole shear flow here, which is the integral meaning the area within the triangle here. So area within the triangle is half into Q1 into B, which comes out to be, you put all the values, comes out to be V square, VV square 2H by H by 6 plus B. Now, this, so there is FF here, which has this value. There is FF here, which has this value. And we know that the vertical is going to be equal to the V that we have, right? Because it will balance, vertical forces has to be balanced, so it will be equal to V. It cannot be something different. So we don't have to calculate that separately. So that is your FW. Now, how do you find shear center? I know my force V here. I know my FF here. I have to make sure that the load is acting from such a distance such that moment from that point for all the internal forces is 0. So you take a moment about this line. It is going to be minus V plus FF into H equal to 0. And then you put all the values for V and H, and you see that E comes out to be independent of V. So E is independent of load. It is a geometric property. Okay. Now for various cross sections, I have a channel section itself, but I have moved it like this, and that's my loading direction. In that case, your shear center is supposed to be on this line, right? If you load it like this, P, then it's not going to have any twist because it's symmetric bending right now. So E is equal to be 0 here. Shear center lies at one of the line of symmetry. Okay. If you have a H section, it has to pass through this point. Here you should apply your P. Okay. Similarly, you can do for many other sections. Please find for a section like this, which is given in the book, a channel section rotated, okay, or an L section, right? Find E. For this kind of sections. How is it going to be in case? The shear flow is going to look like this. This is VY2, FF, okay. All right, now you can see that since there is Vy2 here, this is Vy2 here, you take a moment about this line, this moment and that moment will cancel each other, right? And therefore, your shear center has to be equal to 0. All right. Similarly, for this also you can do it. How is going to be its shear flow? It's going to look like this. Okay, so this is also going to be Vy2, that's also going to be Vy2. Okay, and if both are Vy2, then you can see that they will balance again each other. You have to do for this. First, you have to find how you're going to look like, and then you have to find, it's how you're going to balance it. Will this be like this? Just look at it and try to find it. Okay, that's what we have for shear centers and shear flow. And I hope you have at least have some feeling about shear center. This is one of the design parameter for many of the sections which are not doubly symmetric. For doubly symmetric sections, it will always go through the center point. But for single symmetric sections, since there can be unbalanced twisting moment, they will not pass from the center. They will go through some other point, and you have to find that point. Okay. Right? All right. You can see these diagrams. These diagrams are important. How your channel sections and V sections, how your flow is, and the big clockwise. You see here, bending is clockwise. Okay, and you see that's this change center line will give you same thing. So do it for sections like this. I have done this one. This one is done. Do it for this section. Okay, look at for that. Remember that for any inclined section, it is going to be parabolic. Only for sections that are normal or perpendicular to your loading direction is going to be linear. Apart from that, any other section, it is going to be parabolic. So do not make a mistake there, right? Now let's go back and look at little bit into unsymmetric bending. Since this is the last class, let us unsymmetric bending. Okay, unsymmetric bending. We have seen whatever we have seen in our classes are for symmetric structure, symmetric loading, right? We consider two things. One, symmetric cross section, and two, load along axis. If you remember, this is what we have done. We have a beam. This was our section, so it was a symmetric section, and the loading was acting along this line. Right, along this line. Now, unsymmetric bending can be because of these two reasons itself. Unsymmetric bending is due to one, section unsymmetric, and two, load inclined. Okay, load inclined meaning what? Load inclined meaning again you have that same beam. Okay, and let's say your sectional sorry, line of symmetry goes from this point. Sorry, sorry, I got cold. I think the load goes from some angle here. So load is applied here in format of P. Okay. Now, if I look at the cross section, these are my symmetric line. My P force is going from this point like this. Okay. So in that case, let's say this is my B, this is my H. In that case, what we will do? We will change the cross section. Okay. And the load is like this, which will be equivalent to two sections. One which will be like this. This is going to be P. If this is your theta, this is going to be P cos theta. And plus, I'll also look at another one will be from this axis, right? This will be P sin theta. Okay. So bending for this is going to look like this way. And bending for this is going to look like this way, right? How about that axis? Right? So if I have that, I have to do both side bendings. I have to calculate both side bendings and add them, right? Now, for this kind of sections, our conventions are like this. Okay. This is P cos theta. This is P sin theta. And let's say those are my X and Y axis. So I can write this way. So there will be one moment which will be acting this direction like this. The other moment will be acting this direction like this, right? This is called MZ. This is called My. Is due to P sin theta. and is due to P cos theta. Is that clear? This should be clear to you. Because if you see the bending, P sine theta is going to bend like this, right? So if you look at the moment is along this axis, downside, right? About this axis, but downside. But our y-axis is upward positive, right? So that's why this is my positive direction. This is my z positive direction. Okay. Similarly, this I have discussed already. This one is mz, we call it, because this gives a moment this way. So right hand thumb rule will tell that moment is along this direction. Okay. Therefore, if I choose any point, let's say I choose point this one, positive x and negative z. Okay. This is negative z. If you note, this point is a negative z and positive y. At this point, your stress will be due to y. How is your stress going to be? Sigma x. Due to y, what will be stress? M z into y by I. Okay. Or let us consider a point which is positive both sides. Okay, that will be a better idea. Let us consider a point which is positive x and positive z. Okay, this point is y comma z, positive y and positive z. So at this point, your y is going to be my by I, and remember that there will be a minus sign here, right? This is minus my by I, because upside for this moment, the upward is compressive. So this point or this point, whatever you say, is going to be compressive. So it's minus. Now for the other load, this one, okay, for that one, this point going to be right, and this one I have to write as z, Iz, because now I'm looking for, and this one is going to be my into z iy. Okay, all right. So if I have a moment like that, like this side is positive and that side is going to be compressive. So this side is going to be tensile and that side is going to be compressive. And for the other load, this side is going to be tensile and the upper side is going to be compressive. So you have to look at that very well. Okay, so you have to look at the conditions that you might have here, plus minus, based on which coordinate you are. The sign convention to be chosen based on the coordinate you are. Y comma z. Okay, and another point is now you have to see that since it's going to have different positive, negative, your neutral axis is not going to be, so let me draw that. It will be easier to see the drawing. Okay, now let's say that mz is acting. Mz is acting in which direction? Mz is this direction, right? Mz. So this side is compressive and this side is tensile. Okay, and for the other one, right, and the moment is acting this way, right? Y. In that case, you have this side as tensile and that side as compressive. Okay, therefore when you combine them, this plus this will be equal to something like that may come in, how do I, yeah, line, this line. So it might be something. Something like this, of which that will be your, that can be green portion, this can be your yellow portion, and this can be your green portion. So this will be going to be your, and how do you find neutral axis? Should be sigma x to be equal to 0. Okay, and this line, neutral axis, may not be perpendicular to the load. Remember, this was our first assumption for symmetric loading, that neutral axis is always perpendicular to the load, right? That used to happen when you have a symmetric axis and symmetric load P. Your neutral axis goes to go through this. In this case, it's not going to be like that. Okay. With that, I'll stop because I've taken more than my required time.